Right now, as you're listening to this, an object roughly 5 kilometers across is racing through our solar system at 137,000 miles per hour. Its designation is 3, I Atlas. The I stands for interstellar. It's only the third confirmed visitor from beyond our sun's gravitational domain that we've ever detected. It was first spotted by the Asteroid Terrestrial Impact Last Alert System in Chile on July 1, 2025, at a distance of 420 million miles from the sun. Within 24 hours, something impossible appeared in the data. The object was impossibly bright for its distance. It showed a massive coma of gas and dust. But when astronomers turned their spectrographs toward it, expecting the familiar signatures of sublimating water ice and organic compounds, they found something that shouldn't exist: pure nickel emissions, no iron, and a forward-pointing jet aimed directly at the sun. Let that sink in. I'm Michio Kaku, theoretical physicist. I've spent my career explaining the universe through the lens of physics, always demanding evidence, always following where the data leads rather than where speculation tempts. And right now, the data coming from 3I Atlas is harder to explain than almost any natural object we've encountered. I don't deal in sensationalism. I deal in measurements, orbital mechanics, spectroscopy, and statistical probability. So when I tell you that this object has accumulated 8 documented anomalies that place it at rank 4 on the Loeb scale, a framework designed specifically to quantify the likelihood of technological versus natural origin, I'm not making a claim. I'm reporting what multiple observatories, space agencies, and peer-reviewed analyses have documented between July and October of this year. The detection network that found 3I Atlas represents the cutting edge of planetary defense technology. Atlas, the Asteroid Terrestrial Impact Last Alert System, operates 4 telescopes across Hawaii, Chile, and South Africa, scanning the entire visible sky every 24 hours. It's funded by NASA specifically to find objects that might threaten Earth. On that July morning, Atlas Chile registered a fast-moving dot at magnitude 20 in Sagittarius. Initial orbital calculations showed hyperbolic excess velocity of nearly 60 kilometers per second. That's astronomer terminology for an object that isn't gravitationally bound to our sun. It came from somewhere else. Within hours, archival searches found pre-discovery images extending back to June 14th. The Minor Planet Center issued alerts. Observatories worldwide swung their instruments toward the coordinates. The Hubble Space Telescope captured imagery on July 21st. The James Webb Space Telescope deployed its near-infrared spectrograph on August 6th. Gemini North and Gemini South observatories in Hawaii and Chile obtained multi-wavelength data. The Spherex spacecraft analyzed its infrared signature. Think of this coordinated response as humanity's immune system detecting a foreign body. We mobilized every sensor we had. Here's where it gets interesting. And by interesting, I mean statistically improbable to the point of raising fundamental questions. Anomaly 1, trajectory alignment. 3I Atlas entered our solar system on a path inclined just 4.89 degrees from the ecliptic plane. That's the flat disk containing Earth's orbit and most planetary orbits. Interstellar objects arrive from random directions across the celestial sphere. The probability of random alignment this close to the ecliptic is approximately 0.2%, 1 in 500. Objects from the galactic disk should arrive with inclinations reflecting the 60-degree misalignment between the ecliptic and the galactic plane. Previous interstellar visitors arrived at 123 degrees and 44 degrees inclination. 3I Atlas, nearly coplanar with Earth's orbit. Anomaly 2, the sunward jet. On July 21st, Hubble's wide-field camera captured an image showing a teardrop-shaped cocoon of material. But it wasn't a tail streaming away from solar radiation pressure like every comet we've studied. It was a jet. A collimated beam of gas and dust 10 times longer than it was wide, pointing directly toward the sun. David Jewett at UCLA, who led the Hubble observation team, confirmed this was not an optical illusion from geometric perspective. It was real outflow in the wrong direction. Cometary jets form when sublimating ice erupts from active regions on a nucleus. They can point sunward temporarily due to rotation. but sustained anti-solar jets across weeks of observation? That violates standard cometary physics unless there's directed thrust. Think of it this way. Imagine watching a campfire. Sparks fly upward because hot gases are less dense than cold air. Now, imagine a campfire where sparks flew downward into the logs. That would indicate something pushing them against natural pressure gradients. The anti-tail of 3I, Atlas, observed consistently through July and August by Hubble, Webb, Gemini, and the Nordic Optical Telescope, was material flowing the wrong way. By September, conventional tail behavior resumed as the object approached perihelion and solar heating increased mass loss rates, but for 2 months it defied expectations. Anomaly 3, mass. Based on the lack of detectable non-gravitational acceleration despite significant outgassing, Richard Chloe, Peter Veris, and Avi Loeb from Harvard calculated that 3I Atlas must possess a minimum mass of 33 billion tons. That corresponds to a solid nucleus at least 5 kilometers in diameter, possibly as large as 5.6 kilometers, based on Hubble's August 20th observations. Compare this to one I/Oumuamua, estimated at 200 meters maximum dimension, with a mass roughly 6 orders of magnitude smaller. Compare it to 2I/Borisov, the second interstellar comet, with a nucleus under 1 kilometer and mass 3 orders of magnitude less than 3I Atlas. The size distribution of interstellar objects should follow a steep power law. We should detect thousands of small objects before finding one this large. We've detected 3 total. 2 were tiny, 1 is enormous. That's not how statistical sampling works unless the population we're sampling from is highly unusual. Anomaly 4, orbital timing. 3I Atlas will reach perihelion, its closest approach to the Sun, on October 29, 2025, at 1.356 astronomical units. That's 203 million kilometers, just inside Mars's orbit. On October 21st, 8 days before perihelion, it reached solar conjunction. That means it passed directly behind the Sun as viewed from Earth, rendering it completely unobservable from terrestrial telescopes during the most critical phase of its approach. Its trajectory brought it within 30 million kilometers of Mars on October 2nd. It will pass Venus, it will pass Jupiter. And Earth will be on the opposite side of the Sun during peak solar heating, when any technological system would have maximum power available and optimal conditions for maneuvers. In astronautics, this is called the Oberth effect. The most energy-efficient point to change velocity is at perihelion when orbital speed is highest. An impulse at peak velocity maximizes kinetic energy change. If you wanted to slow down, speed up, or release smaller craft with velocity kicks that would separate their trajectories over subsequent months, perihelion behind the Sun is exactly when you do it. Surface illumination at perihelion delivers 33 gigawatts of power to a 5-kilometer object. That's comparable to multiple nuclear power plants. Is this coincidence? Perhaps, but it's a very convenient coincidence. Anomaly 5, chemical composition. The Keck Observatory's Cosmic Web Imager captured spectroscopic data on August 24th, showing prominent nickel emission lines in the coma. No iron. Every natural comet shows iron and nickel in roughly equal proportions because those elements condense together in stellar environments and are incorporated into planetesimals during system formation. The nickel to iron ratio in solar system comets typically ranges from 0.8 to 1.2. 3I Atlas shows nickel without iron. The Keck team also detected cyanide compounds, but water content estimated at only 4% by mass compared to 80% typical for comets. Webb's near-spec observations confirmed carbon dioxide as the dominant volatile rather than water ice. This is chemistry that doesn't fit standard comet models formed in the outer regions of planetary systems where water ice dominates. Some scientists propose that 3I Atlas might originate from a system where metal-rich planetary collisions created debris with unusual composition. That's possible, but nickel without iron is the composition of certain high-temperature industrial alloys, Inconel, nichrome, alloys specifically designed for high-stress, high-temperature aerospace applications. I'm not claiming that's what we're seeing. I'm stating what the spectroscopy shows and noting that this specific elemental ratio doesn't occur naturally in known cometary reservoirs. Anomaly 6. Polarization. Optical polarization measurements quantify how light scatters off particles in the coma. Different grain sizes, compositions, and structures produce characteristic polarization signatures. 3I. Atlas exhibited extreme negative polarization in early observations, a property unprecedented among comets, including 2I, Borisov. Negative polarization typically indicates forward scattering from large, low-albedo particles with complex structures. The magnitude observed was off the scale for natural cometary dust. Anomaly 7. Activity level. Sphere X observations between August 7th and 15th measured outgassing rates. Webb's August 6 spectroscopy calculated mass loss at 150 kilograms per second at 3.32 astronomical units. That's unusually active for a comet at that distance. Total mass loss between July and October amounts to approximately 2 million tons, which represents less than 0.00005 of the object's total mass. It's shedding surface material at high rates while maintaining structural integrity and showing no detectable trajectory changes from recoil forces. That requires enormous mass or very low effective surface area exposed to solar heating, neither of which fits standard comet models easily. Anomaly 8. Arrival direction. 3. I-Atlas entered our solar system from a trajectory that, when traced backwards, comes within 9 degrees of the sky coordinates where the famous WOW signal was detected on August 15, 1977. The WOW signal remains the strongest candidate radio technosignature ever recorded, a 72-second burst at 1,420 MHz, detected by Ohio State University's Big Ear telescope. The source was never identified. The signal was never repeated despite extensive follow-up searches. Its location in Sagittarius has been recorded precisely. 3. I-Atlas arrived from nearly the same direction 48 years later. Correlation is not causation. Directionality could be pure chance. The probability of arriving within 9 degrees of any specific coordinate is roughly 6.1% of the celestial sphere, not impossibly rare. But combined with 7 other anomalies, it adds to the cumulative improbability. Let me be absolutely clear about what we're discussing here. We're discussing the data, the measurements, the spectroscopy, the orbital mechanics, the statistical distributions. I am not asserting that 3I Atlas is artificial. I am asserting that it exhibits multiple properties that, taken individually, are unusual but explainable, and, taken collectively, form what statisticians call an improbability stack. Each anomaly increases the prior probability that we're observing something outside the natural distribution of cometary objects. Consider 3 scenarios. Scenario 1. 3. I-Atlas is a natural comet from an interstellar environment with formation conditions radically different from our solar system. Perhaps it formed in a system where a metal-rich planetary collision enriched the local environment with nickel-bearing minerals. Perhaps tidal forces during ejection from that system altered its structure. Perhaps its trajectory alignment and perihelion timing are simply coincidental. Perhaps every anomaly has a mundane explanation we haven't thought of yet because our sample size of interstellar objects is 3 and we're extrapolating from insufficient data. This is the most probable scenario given our baseline expectation that the universe is mostly natural objects following natural laws. Scenario 2. 3I. Atlas is a natural object, but one that will force us to significantly revise our models of comet formation, interstellar object populations, and the diversity of planetary system architectures across the galaxy. Its properties represent the extreme tail of natural variation. We haven't seen objects like this before because the population is rare and we've only just developed the survey capabilities to detect them. The Vera C. Rubin Observatory came online this summer and is projected to find 1 to 2 interstellar objects per year. Over the next decade, we'll build a statistical sample that will contextualize whether 3I Atlas is an outlier or representative of a previously unknown population. Scenario 3, 3I. Atlas is a probe, not necessarily from an extant civilization, but potentially an artifact from a long-dead one, a von Neumann machine replicating across the galaxy over millions of years, or an autonomous reconnaissance system deployed eons ago and still functioning. This scenario has the lowest prior probability but the highest consequence if true. It would represent the most significant discovery in human history. It would answer the question we've asked since we first looked up at the stars. Are we alone? Here's the thing about science. We follow evidence, not wishes. The evidence right now places 3I, Atlas at rank 4 on the Loeb scale. That's the category defined as unusual but not conclusive, warranting continued observation but insufficient for extraordinary claims. Rank 10 would require clear techno-signatures. Communication attempts. Observed maneuvers inconsistent with gravitational trajectories and outgassing forces. Geometric structures visible in high-resolution imagery. We don't have that. What we have is a collection of anomalies that don't quite fit. And we have an opportunity to gather definitive data. The International Asteroid Warning Network issued an announcement on October 21st, the day of solar conjunction. They initiated a coordinated observation campaign running from November 27th through January 27th, 2026. The campaign specifically targets 3I, Atlas, to improve astrometric techniques and characterize its post-perihelion behavior. Why now? Because after hiding behind the Sun through October, the object will emerge in late November, traveling outbound at high velocity. We'll have a narrow window to observe whether its trajectory remains purely gravitational or shows deviations. We'll watch for any objects that might have separated during perihelion. We'll monitor spectroscopic changes. We'll track whether the outgassing rates and chemical signatures remain consistent or shift in ways unexplained by decreasing solar flux. ESA's JUICE spacecraft will observe 3I Atlas post-perihelion. NASA's Juno orbiter will contribute data. The Mars Reconnaissance Orbiter's HiRISE camera was scheduled to image the object on October 2nd during close approach to Mars at a resolution of 30 kilometers per pixel. Those images, if released, would show surface details 20 times better than Hubble managed from Earth. But as of late October, those images have not been made public. Whether that's due to government shutdowns, data processing delays, or classification is unclear. Here's what we should watch for. If 3I Atlas is natural, its post-perihelion trajectory will follow a hyperbolic escape orbit with velocity changes explained entirely by solar gravity and outgassing recoil. The International Astronomical Union will refine orbital elements. Spectroscopy will remain consistent with cometary volatiles. The object will fade as it recedes, losing activity predictably as solar heating diminishes. By mid-2026, it will be beyond Jupiter's orbit and too faint for detailed observation. It will leave our solar system forever and we'll never know its origin with certainty. If there's any technological component, we might see trajectory deviations inconsistent with gravity and outgassing. We might detect new objects on divergent paths separating from the primary. We might observe changes in the rotation rate or coma morphology suggesting deployment events. We might, if we're extraordinarily lucky, detect electromagnetic emissions, radio, optical, anything inconsistent with thermal blackbody radiation. The probability of that last possibility is low, very low, but not zero, and that's what makes this moment in history unique. For the first time, we have the technological capability to characterize interstellar objects during their transit through our system. We have space telescopes, we have multi-wavelength spectroscopy, we have spacecraft positioned throughout the solar system capable of opportunistic observations. We have coordinated international networks dedicated to tracking and analyzing these visitors. A century ago, 3I Atlas would have passed unseen. 50 years ago, we might have detected it as a blur on photographic plates, without understanding its origin. Today, we can measure its chemistry, map its surface with radar if it comes close enough, and track its trajectory with centimeter precision. The window is November through January. Mark those dates, November 27th through January 27th. The IAWN campaign will publish astrometric data to the Minor Planet Center in real time. Professional and amateur astronomers worldwide will contribute observations. If you have access to a telescope with aperture above 200 millimeters, you can photograph 3I Atlas yourself and submit measurements. Citizen science has become integral to planetary defense and near-Earth object tracking. Your data could contribute to the analysis. What should you expect? Most likely, we'll confirm that 3I Atlas is an unusual comet that expands our understanding of interstellar small body populations. We'll publish papers, we'll refine models, we'll add it to the catalog of weird objects that make astrophysics endlessly fascinating. The anomalies will be explained one by one as natural consequences of exotic but plausible formation environments. But there's a chance, however remote, that the data from November and December will deepen the mystery rather than resolve it. That's how science advances. Not through certainty, but through the process of eliminating hypotheses until we're left with the explanation that fits all the evidence, no matter how strange that explanation might be. To stay on the timeline as this unfolds, to follow the observational campaign and the data releases in real time, make sure you're subscribed. This channel will cover the IAWN results as they're published. We'll analyze spectroscopic updates, we'll track any trajectory refinements, because whether 3I Atlas turns out to be a comet, an asteroid, or something we don't have a category for yet, it represents a milestone in our species' ability to study the universe beyond our gravitational neighborhood. So here's the fascination question I want you to consider. When you look at the 8 documented anomalies, the statistical improbabilities, the chemical signatures that don't fit models, the trajectory that placed this object behind the sun during perihelion, do you think we're seeing the limitations of our comet formation theories, or do you think we're seeing evidence of pattern where pattern might actually exist? Are we engaging in confirmation bias, finding meaning in noise because we want the universe to be populated with intelligence? Or are we finally developing instruments sensitive enough to detect artifacts if they exist? Leave your thoughts in the comments. Be specific. Are we looking at natural anomalies or technosignatures? This is not a rhetorical question. This is the central scientific question of the 21st century, and 3I Atlas is our test case. The universe is vast. 400 billion stars in our galaxy alone. 2 trillion galaxies in the observable universe. The number of potentially habitable worlds is staggering. The Fermi paradox asks why, given those numbers, we see no evidence of intelligence. Maybe we haven't been looking carefully enough. Maybe the evidence is subtle, requiring decades of false positives before we recognize the real signal. Maybe interstellar probes don't look like silver saucers. Maybe they look like rocks, fast-moving rocks with slightly weird chemistry and inconvenient trajectories. Or maybe they're just rocks. That's the beauty of science. We don't have to guess. We can measure, we can calculate, we can observe. And over the next 3 months, we will. 3I Atlas is currently beyond Mars's orbit, racing outward at 61 kilometers per second. By December 19th, it will make its closest approach to Earth at 270 million kilometers, far too distant to pose any threat, but close enough for detailed spectroscopy. Then it will fade into the black. In 10 years, it will be beyond Pluto. In 100 years, it will be halfway to the nearest star system. In 10,000 years, it will be someone else's mystery, entering someone else's solar system, raising the same questions for whatever civilization notices its arrival. Right now, though, it's ours. Our data, our mystery, our chance to practice the methods we'll need when the next interstellar visitor arrives, and the next, and eventually one that leaves no doubt about its nature. The thing about the universe is that it doesn't care what we believe. It simply is. And sometimes it sends us puzzles wrapped in ice and metal, traveling faster than anything we've ever built, arriving from directions that make us wonder if coincidence is the right explanation. Sometimes those puzzles have simple answers. Sometimes they don't. 3. Atlas reached perihelion on October 29th. It survived. Whatever it is, it's still intact, still outgassing, still following a trajectory determined by forces we can calculate. In a few weeks, when it emerges from solar glare, we'll point every instrument we have at it one more time. We'll measure, we'll analyze, we'll publish, and then we'll know a little bit more about what's out there. Until then, we wait, we watch, we follow where the data leads, because that's what scientists do. We don't jump to conclusions, we accumulate evidence. And when the evidence becomes overwhelming, when the improbability stack gets high enough that maintaining the null hypothesis requires more faith than accepting the alternative, that's when paradigms shift. Are we at that point with 3i Atlas? Not yet, not even close. But we're at the point where we have to take the question seriously, where we have to design observations that could falsify the technological hypothesis if it's wrong or provide support if it's right. We're at the point where ignorance is no longer an acceptable position because we have the tools to reduce uncertainty. The images are hard to believe, the nickel emissions are hard to explain, the trajectory is hard to dismiss. But hard is not impossible. Science is built on hard problems that eventually yield to persistent observation and rigorous analysis. 3i Atlas is our hard problem for this decade. Whatever we learn from it, whether it confirms every assumption we have about comets or forces us to rewrite those assumptions entirely, will advance our understanding of the cosmos and our place within it. That's what exploration means. Confronting the unknown with curiosity and skepticism in equal measure, demanding evidence but remaining open to whatever that evidence reveals. Are we alone? I don't know. But for the next few months, we have a chance to gather data that brings us incrementally closer to answering that question. And that makes this an extraordinary time to be alive, to be watching, to be part of the species that finally developed eyes sharp enough to see interstellar visitors and minds curious enough to ask what they really are. So pay attention. The observation window opens in November. The data will follow in December and January. And somewhere in those measurements, in the spectra and the astrometry and the photometry, might be an answer we didn't expect, or might be confirmation that the universe is exactly as we thought, vast and mostly empty and indifferent to our hopes. Either way, we're about to find out. And that's the most exciting thing happening in astrophysics right now.